Hey guys, Nick here, and today we're going to take a look at the subject of trigonometry, which is the study of right triangles. Now, before we start, I just want to say that trigonometry is an especially intimidating and confusing subject. It's often taught very fast in schools, so I just want to say don't worry if it didn't make sense to you immediately when you saw it. It's not supposed to. It didn't make sense for me immediately, and as a result of that, in this video I want to go through slowly and methodically to hopefully give you some understanding of how you can use trig to solve problems. Now, the fortunate thing about trig is that although it's a deep subject, 98% or maybe even more of trigonometry that you'll do in a science class, let's say a physics class where trigonometry is usually the most useful, it all comes down to two examples, okay? Just two operations that you're going to be doing over and over and over and over. So if you can understand just these two examples, and we're going to do a lot of example problems of these types to make sure you have practice, you're going to be set. So the two sorts of problems, and this is just a preview, we're going to go into it in depth. Case one here, it's going to be you're given the hypotenuse of a right triangle and an angle, and you're going to be asked to find the length of both of the other sides. Now, through trig, this is going to be pretty much a one-step problem for each side. This is going to be the thing that you do probably of the 98%. This is going to be 90% of the 98%. Almost everything you do in physics is going to be breaking up a diagonal arrow slash side into a purely left-right arrow on the bottom, this one, and a purely up-down side on the right. And you're going to want to know what those sides are. The second example case is you're given the length of the two non-hypotenuse sides, so in this case 2 and 3, and you're asked to find the length of the hypotenuse, which you can actually just do the Pythagorean theorem for, so that's not really trig. But finding this angle right here, theta, that's something that you're going to need to use trig for. So we're going to cover that example in detail as well. This is going to be useful in physics for an example question of someone walks to the right 2 meters and then forwards slash up 3 meters. What angle are they relative to going to the right now? And that's a question that we'll use trig to answer. So like I said, I'm going to show you how to do both these cases of problems as well as some other problems you might run into. And we're going to do a lot of practice on examples. This subject is probably, of all the subjects out there, the one that doing examples benefits most. So we're going to do a ton of them, and we're going to learn through those examples. Now, something I want to say before we start is a note about your calculators. You might already be aware of this, but if not, make sure your calculators are in degrees and not in radians. Okay, and I'm actually going to put this in Galaxy Pen because it is extremely important. You'll get problems wrong, but not know that something's wrong until it's too late. And the reason I really want to point this out is radians is often the default setting on calculators. Okay, and this means that if you wipe your calculator before an exam, you need to check again because often it'll reset you to radians. Okay, so just be really aware of that. Okay, now let's start with the point of trigonometry. What does trigonometry tell us? It's going to mostly allow us to do two things. It's going to allow us to, one, find the side lengths of right triangles. So that's sort of example one up here, where you're told the hypotenuse and an angle and you're asked what are the other two sides. That's case one. And trigonometry will also allow us to find the angles in right triangles if we know the side lengths. So I'll say the first one is given an angle, and the second one is given lengths. Okay. Now let's do at first a calculation that will illustrate how you can use trigonometry to find an unknown side length. So we're going to do this in the context of an example, like a lot of things in this. So here's a right triangle. I'm going to tell you that the hypotenuse is length 50, and this angle, is of size 30 degrees. And the question that we're going to work on is, what is the length of this side? Okay. Now, if you were given the length of this side too, you could use the Pythagorean theorem to find that side, but you're not. Instead, you're given the angle, and that indicates that you're probably going to need to use trigonometry. Trigonometry allows you to jump between angles and lengths, right? If you're given the angle, you're guaranteed to know the lengths. If you're given the side lengths, you're guaranteed to know the angles. Okay? Now, what trigonometric functions on your calculator will do, and your calculator is going to be indispensable here, by the way. Your calculator's sine, cosine, and tangent buttons will spit out not really the length of sides, but the ratio, so the division of two sides. Okay, so let's imagine that I were to tell you the information about this triangle. Let's imagine that I just told you out of the blue. I'm not going to tell you how I got it. It turns out I'll get it from my calculator, but I'm not going to tell you how. Let's say I just told you this side is half the length of the hypotenuse. Okay, let's say I just told you that. Oh, the scroll bar is not going to let me close my quotes. If I were to tell you that this side that we're searching for right here is half the length of the hypotenuse, this would be an awfully easy problem, wouldn't it? Because if you know that this side is half the length of the hypotenuse, and the hypotenuse is of length 50, then it's pretty obvious that this side would be of length 25. Now, the only question is, how did I get this number that it's specifically 1/2 the length of the hypotenuse, and not 2/3 or 75%? So, the only real question is, how did I know, or how did I ask my calculator that the unknown side was exactly 1/2 of the hypotenuse and not some other number like 2/3 or 3/4? How did I get that exact number 1/2? And it turns out the answer is, it's all going to be about knowing what buttons to press on your calculator to ask your calculator to spit out one of these numbers, depending on what the angle of the triangle is. So, as an example, there's a button on your calculator called sine, and you feed it in an angle. And what this is doing is it's going to the calculator, which knows what right triangles look like. Basically, someone has built a bunch of right triangles and recorded how big their sides are relative to each other. So when you type in sine and then input an angle, what it's saying is, hey calculator, tell me how big the side opposite the angle is relative to the hypotenuse. So in our example here, if you punch in sine of 30, you're asking the calculator, hey calculator, tell me what this side over this side is. And the calculator, again, has a picture of a right triangle in it. It looks at it, it measures what the sides are, and it tells you, oh, I got you, man. It's 0.5. 0.5 is how big that vertical side is in a 30-degree triangle over the hypotenuse. Okay? Again, what this is doing is when you punch sine of 30 into your calculator, you're asking the calculator, hey man, help me out here. How big is this side over this side? In the last example, Nick told me it was 1/2, but Nick happens to forget what the number is right now. Can you tell me if this side is 1/2 the length of the 50, or 2/3 the length of the 50, or 3/4? And the calculator says, I got you. When you hit equals on sine of 30, it says the ratio of those lengths, it's 1/2. And that allows you, just in the same way before, where once I told you that this side was 1/2 the length of the hypotenuse, now you have that number 1/2, and it becomes an easy problem, right? The calculator has told you by outputting 0.5 what the calculator tells you when it outputs that answer is this side is 0.5 times the length of the hypotenuse. Oh. Okay, and again, technically, your calculator phrases it as the division of the unknown side by the hypotenuse, but it's the same thing as the side being half the length of the hypotenuse, right? If you have this side over the hypotenuse is 1/2, that's the same thing as saying that this side is half the length of the hypotenuse, just phrased in a way that's less understandable. Okay? Oh, the scroll bar is going crazy here. Okay. Again, just to recap one final time, because this is probably the thing that is most difficult to understand and the thing that holds you up the most, is by punching sine of an angle into your calculator, you're asking your calculator a question. You're asking it to tell you how big this side is relative to that side, and the calculator will tell you. And in this case, the calculator told you the ratio of those two sides is 0.5. And as soon as you had that number, you knew how to go find the unknown side, because it told you unknown side divided by 50, that is equal to 1/2 in this case. Now, your calculator knows more than just the case of a 30-degree triangle, and that's what makes Trig so strong. Your calculator knows the ratio of these two sides for any angle of elevation right here. So let's do an example with a different side length, okay? All right, let's take a triangle, again a right triangle, with hypotenuse length 34 and angle 38 degrees right here. And again, the task is, what is this side? Now, since this angle is 38 degrees, it's no longer going to be 1/2 of the hypotenuse. It's going to be some other number. It's probably going to be a little bigger because this vertical side is a little taller now that I've made the angle bigger. But Off the bat, we don't know what it is, but our calculator does know. It has it stored somewhere how big this side is relative to this side. So we're going to ask the calculator, hey calculator, can you tell me how big this side is relative to this side? And if you punch in sine of 38 on your calculator, I'm doing it right now, you get 0.62. So this is your calculator responding, I got you, man. The opposite side is 0.62 times the length of the hypotenuse side. And as soon as you have this information, now you're just going to be able to do some multiplication to find the length of the unknown side. Now, in equation form, remember, you can write this as the unknown side over the hypotenuse side is equal to 0.62. This is the same thing as saying that the unknown side is 0.62 times the hypotenuse. Right? It's just phrased in a division. This is the standard way to phrase it. Okay? Now, we know what the hypotenuse is. It's just 34. So all we need to do is multiply both sides by 34 to get our answer of 21.1. Oops, I have some old notes down here. Okay, so that tells us that the unknown side is 21.1. Right? Again, just a recap. As soon as you know how big this side divided by this side is, you're golden. The way you ask your calculator to tell you how big they are relative to each other is you punch in this command, sine of 38 degrees. Your calculator goes, it draws a picture of a 38-degree triangle, and it spits out, oh, I got you, man. This one is 62% the size of 34. And as soon as you have that, you know instantly how big it is. You just find what 62% of 34 is, which is effectively what we did when we solved this equation. Okay? And as soon as you had that, you multiplied out by 34, and you found the length of the unknown side. So it was basically the only step of the problem was knowing to punch sine of 38 into your calculator. After that, all it was is one step of multiplication. All right, let's do another example like this. Oh, I'm sorry, I need to clean up the previous edition of the video where I didn't like my explanation enough, so I redid it. Okay, let's do one more example where we're finding the vertical side. Okay. This time we're going to do 42 degrees. We'll have a side length of 60, and as always, this is a right triangle. And the question is going to be, what is the length of this side? Now, all you need to do is remember that the sine button on your calculator, if you plug in 42 into it, it'll spit out a number. So we'll later find that this is equal to, I don't know, 0.6 or something. I'll figure out what actual number it is in a second. Okay? What that number will be is the unknown side that we're hunting for divided by the hypotenuse side, which is 60. Okay? Now all that remains is to find what number sine of 42 is. If I plug sine of 42 into my calculator, I get 0.67. So on this side, I just replace sine of 42 with 0.67. Right? Again, this is your calculator speaking back to you. You asked it, calculator, what is this side divided by this side? Is it 30% the length of the 60? Is it 40%? Is it 67%? And your calculator spoke back to you, I got you, man. It's 67%. Now, go find what the opposite side is using your basic algebra. Okay? Once it spat you out that number, all you had to do was multiply both sides of this equation by 60 to get that the opposite side is 60 times 0.67 is 40.2. Okay? Now, I want to write this out in standard notation for you guys, so maybe you'll understand what you saw in math class or what appears on formula sheets. So the standard notation is sine of an angle. So I'll draw this in our triangle. Sine of some angle, you can plug in any number for theta. Depending on which one you put in, it's a different triangle. And it will tell you the length of the side opposite theta over the length of the hypotenuse. Okay? In our examples, let's say in the example we just did, we plugged in sine of 42 degrees, and what it told us was, the calculator spoke back to you and said, hey man, length of the side opposite the 42 degrees that you want, that divided by 60 is equal to, and then the calculator looked up, it's searching, it says, okay, 0.67. Now just solve this equation by multiplying, and you've got the side length you want. Congratulations. So your calculator is helping you out by answering that question. Okay? And in truly standard notation, what you'll see on formula sheets is sine of theta equals op over hyp. This stands for length of opposite side divided by length of hypotenuse. Okay? But what it means is what I had right here. Sine of some angle will output the length of the side opposite that angle. So it'll output this side divided by the hypotenuse. Okay, and let's do one more example just for good measure, actually. Okay, we're going to have a right triangle of length 67, an angle of 72 degrees here, not drawn to scale because I'm bad. And the question again will be, what is this side length? Now, at this point, I want you guys to pause the video, see if you can do it yourself by punching in sine of 72 in your calculator and solving the equation. And at that point, unpause the video and check if you've done it right. Okay, so as usual, the question is, oops, what is this side? Okay, now if you pause the video, you're coming back. So again, we're trying to find the length of this side. And we know that the sine function in our calculator, if we plug in 72 degrees, our calculator will tell us what the unknown side is divided by 67. Okay, and if you actually ask your calculator to look up what is sine of 72, calculator goes, it builds a 72 degree triangle, and it tells you, I'm going to output 0.95, telling us basically that this side is 95% the size of 67. And again, that's written in this unfortunate division notation instead of multiplication, which makes more sense, but this is the way it's done in class. But anyway, it's the same thing because we're just going to cross multiply to find unknown anyway. So all we got to do now is find unknown. So we're going to multiply both sides by 67. Okay. And that tells us that unknown, is 0.95 times 67 is 63.7. Excellent. That's the length of this unknown side. So here we can fill it in our picture, 63.7. And again, I did not draw this to scale. In reality, it probably looks like that. So this side and this side are pretty close in length because it's a very steep triangle. Now, there's multiple tables, as I had mentioned earlier. There's another table called cosine, and that will answer the question, how big is this side, the side next to the angle, rather than the side on the other side of the triangle from the angle. Okay, that's called cosine. Now, I'm not going to do this example because the triangle has two sides that are the same length. So I'm going to cook up another example, and we're going to attack it using cosine instead. Okay. Now again, before, the sine of an angle was telling us the opposite side, so the side opposite the angle. So it was telling us this side divided by hypotenuse. This time, the cosine function is a different lookup in your calculator, and it's going to tell you the length of the leg next to the angle divided by the hypotenuse. So in the previous questions, I was asking you how big is this side opposite the angle that I told you. And sine would answer the question of how big this is. Cosine will more directly tell you how big this side is. So cosine tells you the adjacent side over the hypotenuse. And once again, cosine of an angle will just spit out a number, and if the number happens to be 0.6, it tells you that this side length divided by this side length, the hypotenuse, is equal to 0.6. So let's do an example with a triangle of hypotenuse 17 meters and an angle of 36 degrees. Okay, so we're just going to write out what this formula becomes for our angles and our side lengths. So the cosine of 36 degrees, that will tell us how big this adjacent side is, which we don't yet know, divided by the hypotenuse's length, which is 17 meters. Now again, this is nothing more than a number. If you punch it into your calculator, cosine of 36, you get 0.81. So it's kind of telling you that this side is like 80% the length of this side. So all you have to do is multiply it out. So multiply both sides of this equation by 17. And you get 13.75. So the answer for how big this side is it's 13.75 meters long. Great. Now guys, here's the mind-blowing part about trig. What if I told you that in these two examples, we have done the thing that is what you do 98% of the time in physics and in the real world? 98% of your calculations that you do in physics are going to be being given the hypotenuse and one angle and finding what this side is and what this side is. So one of them you use sine to find the length of the side opposite the angle, and for another one you use cosine to find the length of the side adjacent to the angle. That is 98% of what you'll do with trig. So if you've made it this far, even if you're just starting to see where it's going, well done. Well done. Okay, now at this point I want to tackle the last trig function, which is called tangent. So sine looked up in the calculator what is the opposite over hypotenuse ratio, so what fraction of the hypotenuse's length is the opposite side's length. Cosine told us a different ratio. It looked at the triangle and it spat out how big the adjacent side was relative to the hypotenuse. Tangent is going to do something a little strange, which is why we don't use it as much. It actually is going to spit out the side opposite the angle divided by not the hypotenuse, but the adjacent side's length. So for example, if we have 38 degrees here, before we were using sine to find this when we knew the hypotenuse, because sine told us opposite over hypotenuse, but here tangent is going to look up how big this side is, the opposite side, relative to this side down here. Okay? So for example, if I take tangent of 38 degrees on my calculator, it's again going to spit out a number, and it happens to be 0.78. So it's telling me that this side right here is 0.78 times the length of this side. Okay? So that would be Actually, let's turn this into an example. Let's pretend I told you that this side has length 20 meters, and I ask you, how big is that side? Now, tangent of 38 degrees tells you this side's length, which we don't know, so we'll leave it as a variable, divided by the adjacent side's length, which is 20. And again, tangent of 38, when you plug it into your calculator, is just 0.78. So it tells us that the opposite side length is 20 by 0.78, which is 15.6 meters. So using tangent, we figured out how big this side was without needing to know what the hypotenuse was. Basically, your calculator has a bunch of tables punched in there. You don't need to know every side. You only need one side and one angle, and your calculator builds the triangle, and it tells you how big all the sides are. And tangent is going to tell you how big these two sides are relative to one another, rather than the hypotenuse. Now, at this point, I want to bring up something that might have caught you off guard during cosine, and it's a question of how did I know that this was the adjacent side length and not this? Okay, yeah, you're right. They are both next to the 38-degree angle. So how did I pick which one was adjacent? And the answer is kind of hidden in notation. The adjacent side is not the hypotenuse. Okay, adjacent sort of implicitly tells you it's the side next to the angle that is not the hypotenuse. That's what adjacent side means. Okay, so in this case, sorry, I forgot to draw the right triangle angle. This side opposite the right angle is the hypotenuse. It always is. So the adjacent side always refers to the side that is not the hypotenuse. In the cosine example, it was pretty clear because the hypotenuse was already involved, so you only had one choice left over for the adjacent. But here, it might have been trickier for you to decide which one. Again, this is hidden in the notation. You shouldn't have known it off the bat. Hypotenuse is off by itself, and the other two legs, as they're often called, are the adjacent, and the opposite leg are not the hypotenuse ever. Okay, great. Now, at this point, I'll do a summary equation because these are seen everywhere. So we had sine of an angle. I'm just going to call an angle theta. That's traditional. This just means an angle. If you punch in an angle into the sine function, so if you put in sine of 30, it'll spit out a number. And what that number is the length of the opposite side of the angle divided by the length of the hypotenuse. The cosine function, if you punch, let's say, cosine of 38 and it spits out 0.6, what that number is telling you is the length of the adjacent side, adjacent side divided by the hypotenuse. And if you plug in tangent, again, this is the weird one that we just covered, it'll tell you the length of the side opposite the angle divided by the length of the side next to the angle. Okay, so these are really the relations to remember. This basically keeps you from accidentally flipping opposite and hypotenuse or adjacent and hypotenuse. Just having it in these nice equation forms with the fractions. Really commit these to memory. Now, fortunately, there is an acronym for these, which you might have heard before. It's called SOH CAH TOA. And this is just to help you remember. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Really, TOA is the one to really remember because the hypotenuse usually appears in the bottom for the other two, but it isn't really clear what should go in the denominator unless you remember this one. Okay, now at this point we're going to move on to the second major thing that you'll do in physics that comprises probably of the remaining 2%, probably 98% of that, you'll only be doing this one other thing. And that is sort of going in reverse, and it's going to be about finding angles rather than finding side lengths from angles. So I'm going to title the section Finding Angles, and the things that you will use are the inverse trig functions or the arc functions. For example, arc sine, which is often written as sine to the -1 on your calculator, that will be the function that you ask your calculator, hey, I told you what these sides are, now tell me what the angle opposite this side is. Okay. Now again, let's do this with a motivating example. Let's say you were told someone traveled 4 kilometers to the right, followed by 3 kilometers upwards. And you asked what angle above the, I guess, the rightwards axis, what angle did they move at net? So for example, if someone asks you, look at them, how far away from rightwards are you looking? How many degrees tilted counterclockwise are you looking? Now, how you would do this would be using an arc trig function or an inverse trig function. So let's see if we can write out one of the trig equations and see if we can get anywhere with it. So right now we're asked about this angle, and we're told the length of the side opposite it, and we're not told the length of the hypotenuse, we're told the length of the side adjacent to it. So if we look up in our equation bank here, tangent has those two in there. So let's write it out and see what we get. So tangent of the unknown angle, which we're trying to find, that will be equal to the length of the opposite side over the adjacent side. So the length of the side opposite the unknown angle is 3, and adjacent to the unknown angle is 4. So the question becomes this. So this is equal to 0.75. The question becomes, what angle would give me tangent of the angle equals 0.75? I sure wish I knew that. And fortunately, your calculator also has this information stored in a table. Okay? And the way you access this information, what angle would give me a tangent of 0.75, would be by doing this. So schematically, we have tangent of our unknown angle that we wish we had equals 0.75. And you would, again, this is sort of a rough idea, you're going to take the inverse tangent of both sides. Okay? Inverse tangent and tangent more or less cancel out. The inverse tangent will spit out the angle. If you take the tangent of an angle, that spits out a number like 0.7. If you take the inverse tangent, it'll spit out the number that you originally put in. So what you have left is your unknown angle is tan -1 of 0.75. Again, this is not 1 divided by tangent. That doesn't really mean anything. this is a separate table lookup in your calculator. Just confusingly named tan negative 1. And if you punch this in your calculator, now usually you want to press the second button and then tan, and then you type in 0.75 inside the parentheses and you hit enter, it'll give you 36.87 degrees. And that's your answer here. That actually is how big this unknown angle was. You just found it using this inverse trig way. Now again, just a recap of how we got there. We knew we were hunting for this angle, but we didn't know what it was. However, we knew we had the opposite side to the angle, and we also had the adjacent side to the angle. So we looked here and said, hey, tangent has opposite and adjacent. I wonder if we can use this equation. So we wrote it out. Tangent of our angle was our opposite side of 3 divided by our adjacent side of 4, which just equals 0.75 when you simplify 3/4. And we were left here, and we were kind of like, we look a little stuck here. And then we did the new thing, which I just told you for the first time how to do, which is you can take the arctangent, the tan negative 1 of both sides, and what that will do is your calculator will answer what angle, when I plug it in here, gives me the right ratio of the two sides. What angle, when I plug it in into tangent, outputs 0.75. And it turns out that that angle is 36.87 degrees. If you want to, you can go check that tangent of 36.87 is equal to 0.75. Excellent. So that's your first flavor of arc trig functions. And again, this is essentially all of the other 2% of trig you'll do, at least in physics and engineering. So if you've made it so far, once again, even if you're still a little unsure about this, we've only done one example. We're going to do some more in a second. You've got what it takes, basically. Don't worry if it isn't 100% yet. You're going to get this. Okay, let's do just a barrage of examples now. I think we're probably going to do, we'll see. It's going to be between 5 and 10 examples right here. So let's get cracking on it. I'll write this in our fancy Galaxy because for this, I swear guys, examples are really important, and with just a couple examples, you're going to get this. Okay, now I'm going to mostly keep the examples to the two cases that you'll see in physics. There really isn't much else, and hypothetically, you know how to do it all already, but we're really going to focus on the common scenarios because you're going to be doing these so often that it's just important to get it down pat, to really understand how it flows, and to get fast at it. So we're going to start off with a typical example of a force arrow going up and to the right. Now, you don't really need to know if it's an arrow or not. You can just treat it as a line. Okay. We're going to say that a problem tells you there's a force going upwards and to the right of size 42 newtons at an angle of 32 degrees above the horizontal. Okay, and again, since you're breaking it into left, right, and up, down, it's a right angle between left and right and up and down, obviously. The first question will be, what is this side? So how much of the force is pointing up and down? And the second question will be, actually, I shouldn't call these x and y. That's going to confuse people. I'm going to call it, shouldn't call it a either. I'm going to call them s and t. So what is side S and what is side T's length? So how much of the force is up and down and how much is to the right and left? This is part of the 98%. You're going to do this in so many problems that once you get this, you're really going to have the dividends pay off. Okay, so if you want, you can pause the video now, take a crack at it, see if you can find how big S and T are. And then you can let the video play through, see if you got it right. If you had trouble, feel free to unpause the video and take a look and a walkthrough and see how I do it. We're going to do another one like this right after. Okay, so for side S, we're given this angle, we want to find the opposite, and we have the hypotenuse. So we have opposite and hypotenuse. So if we go up to our bank here and we're looking for which trig function we might want to use, sine has opposite and hypotenuse. Okay, so the sine, when we plug in 32 degrees, it's going to tell us how big the side opposite that angle is, so S over 42 is. Okay, we multiply both sides by 42 to bring S by itself. So S is 42 times the sine of 32 degrees. Again, this is nothing more than a number. If you plug this in your calculator, you get 0.53. So that tells us that side S is 42 times 0.53, which is 22.25 newtons of force. Now again, don't worry about the units. It's sufficient if you had a triangle of length 42, that's fine. You don't need to do this problem with meters or kilometers or newtons. It works the same no matter what unit there is. All right, now let's attack side T. Side T. So now again here, we are looking for the adjacent side. We have the hypotenuse, so adjacent hypotenuse, which one has that? Cosine does, adjacent on hypotenuse. So if I plug in, actually I'm going to move the work up here so we can see it. The cosine of 32, when we plug that number in, our calculator will spit out a number, and it'll tell us how big the adjacent side, which is T, is over the 42, or over the hypotenuse, which is of size 42. Okay, so again, we move the 42 over by multiplying both sides by 42. And if you plug this in your calculator, 32, you get 35.62 newtons. Excellent. So that was actually your first practice example of decomposing a diagonal force into a left and right force. That's this one, T. And this up and down force, which was of size 22.25 newtons. And that's a phenomenal job, guys, because this is what you're going to be doing with trigonometry in physics. And this is honestly the most important thing out of trigonometry as a whole. This idea of knowing how to break down a right triangle into its sides. All right. Now, I want to point something out here, guys, that first of all, once you have found this side, if you wanted to, you could actually find side T using the Pythagorean theorem. You don't have to do more trig to get this. Now, usually this way will be better for reasons that I won't explain right now, but in physics, very often you're going to have, or I guess I kind of will explain it right now. Very often you'll be told a force acts here, but you won't be told its size. So it'll be very good if you'll leave it, you'll break it down using trig functions on both directions rather than using the Pythagorean theorem. For example, instead of 42 cosine of 32 being on the bottom side, you would then have f of unknown size times cosine of 32. And again, on the vertical side, instead of 42 times sine of 32, you'd have the unknown force of size f times sine of 32 on that axis. This is how you'll, in practice, do it in physics. Don't worry if it makes no sense right now, but in the future, you'll do this. Not the Pythagorean theorem. Okay, now we're going to actually reuse this same example, and I'm going to show you another way to do it, because in trigonometry there's a lot of different ways. Like I said, there's the Pythagorean theorem that we didn't even use until a second ago. We didn't even use it, but I told you could have used it to find S. There's another question that comes up, and it's, what if instead of using 32, I calculated how big this angle was, and then tried to use trig on that angle to find the side lengths? And the answer is that's totally fine. It's 100% workable, and we're going to do that right now to show you that it's totally good, and also to get you used to using angles that aren't in the bottom left. So Q2, we're going to redo question 1, but instead we're going to work off of the other angle. Okay, now this might be a little tricky because, again, what side is the opposite and adjacent have swapped, but we're going to stick to our guns, take it slow, and walk through it. Okay, so we have 42 on the hypotenuse, and we have 32 degrees down here, and the right angle here. So first off, let's find out how big this angle is. So the angles inside a triangle should add up to 180 degrees. That's just some theorem from geometry. So this, or alternatively, this angle and this angle had better add up to 90. That way, this 90 degrees brings it to 180 total. So this angle right here is of size 90 minus 32, which is 58 degrees. Oops, 58 degrees. So we're going to clean up our triangle, write that in. 58 degrees. Oops, can't write. And again, we're going to redo the problem and see if we can find what side. Did I get the labeling right? No, I got it wrong. Just want to keep the same letters. T, S. We're going to work off of this 58 degrees, treat that as the angle, and see what we can do. Okay, let's find side S first. And now again, we're using this angle here. So side S, you guys can ask yourself, is it right now, is it the adjacent side to the angle, or is it the side opposite the angle? It might not be the same as it was before. So if you look at the picture, now S is not opposite the angle anymore, because we're looking at a different angle. S is the side right next to the angle that's not the hypotenuse, so S is actually the adjacent. So for part A of the question, when we're looking for S, we want the adjacent, and we're given the hypotenuse. So if we scroll up, adjacent hypotenuse, we should probably be using the cosine formula again. Okay. So we're just going to write out our equation, cosine of 58. That'll be a number in our calculator, and when we get that number out, it'll tell us how big the side next to the 58 is, so S, divided by the hypotenuse is. Okay, again, we're going to multiply both sides by 42. That'll cancel out the division by 42. And if you plug this in, 42 times cosine of 58, we get 22.25 again, which is excellent because it means no matter whether you choose to use this bottom left angle as your reference angle or this top right, as long as you correctly name which things are adjacent in the hypotenuse and opposite, you'll be able to get it right. Okay, for part B, let's get side T again. Again, T is the opposite side of the angle. We're after that, and we have the hypotenuse. And we search for which side is opposite in the hypotenuse. That's sine. So sine of 58, once our calculator spits out whatever number that is, it'll tell us how big side T is divided by 42. Again, we multiply both sides by 42. and we get, oh no, and we get 35.62 once again. So great, we found both sides are in agreement with what we had done last time, which is awesome. Okay, let's do another example here. This time, we're going to be breaking up a diagonal arrow that this time goes down and to the left instead of up and to the right. Okay, so the right angle is going to be in a different place. And again, this is a model for a force that pushes diagonally down and to the left. Later when you cover it in physics, you're going to be tackling this quite a bit. But you don't need to get that right now. It's something pointing diagonally down to the left. We're going to have it be of size 35. And I'll call it 35 newtons of force. A newton is just how strong a push is. It's a unit of force. And we're going to say it acts in this orientation. 26 degrees, sort of south of west, or I don't know how you would call this if you weren't using a map, but in this orientation. So instead of pointing up to the right, it's pointing down and to the left. And importantly, the hypotenuse and the right angle are in a different place now. Okay, and my question is going to be, what is S and what is T? Again, in physics, the thing you're going to be doing 98% of the time is breaking down this diagonal arrow into its left and right component, and then its up and down component, finding out how big those are. Alright, first let's tackle S. Okay, so we're given that this angle is 26 degrees. Now again, you could hypothetically find what this angle is and do it off that, which is fine. We just did that in the last example. But just for this example, I'm going to choose to use this one. Okay, so S is the side next to the 26, which means it's the adjacent, and 35 is the hypotenuse. And the cosine formula uses adjacent and hypotenuse. So cosine of 26, when I put it into my calculator, whatever number that spits out is going to be the size of side S divided by the size of the hypotenuse, which is 35. So if I rearrange this equation, multiply by the size by 35, I get S is 35 times the cosine of 26, which is 31.46 newtons. Excellent. So that is a force of size 31.46 newtons, and it is pointing to the left. Once you get there in physics, you'll consider which direction things point. But the size of side S, the length of the side, is 31.46. And now for T, so T is the opposite side. We have opposite and hypotenuse. We probably want to use sine. So sine of 26 degrees will tell us what side T is divided by the hypotenuse. Again, you rearrange this, multiply both sides by 35. Plug this in your calculator. And 15.3. So this diagonally downwards 35 newtons force is the same thing as a 31.46 newton force to the left, and at the same time a 15.3 newton force down. Excellent work, guys. This is a killer example. Alright, let's do one example with variables, because very often you won't be told the size of the hypotenuse. You'll just leave it as a variable to be substituted in later, or you might be asked to find what that variable is, so you're not going to be able to put in a number yet, but that's fine. Now, I've actually technically already done this up above. But let's say you have a force pointing up and to the right of size F, which you aren't told, and it's directed as such with 30 degrees above the horizontal. First question would be, break down this force. What is this vertical side right here? Well, this is the side opposite the 30-degree angle, So the size of the opposite, oops, sorry, I shouldn't jump that far ahead. We quote-unquote know the hypotenuse. It is still a variable, but we want an expression involving it, so later we can find what f is. If you were in a physics problem, at least, you'd be able to find what the number f was later in the problem. But so we know the opposite side, and we have a variable on the hypotenuse, so we want to use sine, because sine involves those two. So sine of 30 would equal the opposite side length over the hypotenuse, but the hypotenuse we know is length f, so you multiply both sides by the unknown number f, and you get that the length of this opposite side is f sine 30. So right here, it's f times the sine of 30. And you don't have to punch in what sine of 30 is into your calculator if you don't want to. Similarly, you'd then need to know what's this side. So this is the adjacent side. So we probably want to use cosine. And cosine tells us the adjacent side length, which is just unknown circle right here, divided by the hypotenuse, which is of length f. Again, we multiply by this unknown number f on both sides, and it becomes that the adjacent side, which we want to know, is of size f cosine 30. So here, we would write f cosine 30. And great, now you've broken this unknown force into its up and down and left and right components, which is, again, the 98% of problems you will do in physics involving trig. Excellent. Okay, lastly, we're going to be doing one of the 2% problems. So what example is this? Question 5. So yeah, it won't be 10 examples, it'll be 5 examples with multiple parts. In this case, instead of being given the hypotenuse and the angle and finding both sides, we're going to be given both sides. So we're going to call this, let's say it's a 50 newtons upwards push and a 70 newtons rightward push. And the question would be, what's the size of the hypotenuse? That's known as the magnitude of the force. And question B would be, what is this angle? Now, to get the hypotenuse, you might first want to use trig, but then you remember that, oh, you don't actually need to use trig, and in some senses you can't really. You'd need to find the angle first, which you could do. But it's quick to use the Pythagorean theorem. Right? The Pythagorean theorem says that if you add up this side squared plus this side squared, so again the sides that are not the hypotenuse, you add them up while being squared, that'll tell you what the hypotenuse is squared. So if you add up 70 squared and 50 squared, you get 7,400. And you take the square root of both sides, and you get 86.0 out. So the net size of this force pointing diagonally is 86.0. Okay, and the last question we'll do is, what's this angle? Now again, we recall from the it's way up here. From the red text up here, that when you're searching for angles, you want to use these arc-trig functions. So you want to use arctan or something like that. Arctan spits out an angle. Now again, we're looking for this angle. We are told the length of the opposite and adjacent sides. Technically now we know the hypotenuse, but let's pretend we didn't. So we probably want to use tangent for this. So tangent of this angle, we don't know what it is, we're trying to find it, will equal the length of the side opposite the angle, so 50, divided by the side next to the angle, 70, which is, so 50 divided by 70 is 0.714. So we end up in this scenario of, which angle, when I plug it in here, would output 0.714 as we need. And we know that a way we can have our calculator do this is we use those inverse trig functions on both sides to quote-unquote cancel out the tangent. And you're left with then theta equals arctan of 0.714. Again, what this does is in your calculator, it looks up what angle, when you plug it in, gives you a tangent of 0.714. That was what the angle that's of the proper size should output. And when you plug it into your calculator, arctangent of 0.714. Again, arc functions always output angles. You get 35.5 degrees out. Excellent. Now, actually, I lied. I want to do one more example with arctangent because you do use this rather frequently. Okay, we're going to be told you have a displacement of 30 kilometers to the right, followed by 100 kilometers to the north. And we're going to ask, what is this angle right here? Now again, at this point I want you guys to pause the video, see if you can figure out the angle. Oops, sorry, I should say this is right triangle. Figure out the angle yourself using arctan, and then come back and check if you did it right. Okay, so we're given the side opposite and adjacent to, again, not the hypotenuse, the adjacent leg to the angle. So we probably want to use the formula involving tangent. So tangent of an angle, which we don't yet know, will tell us the opposite side, so 100, divided by the adjacent side, 30. Okay, and 100 divided by 30 just equals 3.3. So we get stuck at this spot, and we want to know, oh, what is theta? What angle, when we plug it in, gives tangent of theta equals 3.33? And as usual, the trick is you get the tan off of it by doing this arctan stuff. So the unknown angle that we want is going to be the arctan of 3.33. And if we plug that in, you get an answer for the angle of 73.3 degrees. Awesome. And that kind of makes sense. This vertical leg, I didn't draw it to scale here. The vertical leg is very tall compared to the horizontal leg, so it makes sense that this angle is close to 90 degrees. All right, excellent, guys. That about wraps up the examples in the video. Now, again, this is a really sensitive topic. It really depends on each person's preferred method of hearing it explained. So if you have questions, if you think I could benefit from including an alternate wording in the video, please do let me know. It'll help out a lot of people. Don't hesitate to comment or shoot us a message. All right, guys, that'll be it for today. Great job today. Congratulations on learning a bit about trigonometry, and I'll see you in the next video.